So head out like, you know.
Let's see, we got all 12 of us showed up today.
Woo!
On what day?
Today.
Like next week.
Cool.
Yes.
All right.
It's the last day of the work week.
So we were making our way through chapter 6, and we'll probably wrap up chapter 6 and move into chapter 7. 7 and 8 I kind of mash up with chapters 11 a bit also, just because for some reason they move the important bits out there. I don't really know why, but that's just kind of the way they do it. But I'm going to draw in some parts of chapter 11, and I'll kind of talk to you guys about what parts it is when we get there. But what we've been going through is just kind of figuring out where the electrons live. We've been figuring out where orbitals are and what they tell us, and how to walk through the periodic table and get our electron configurations, okay? Because our electron configurations are going to tell us where the electrons are, and the electrons are the things that do chemistry, right? And that's what we've been talking about all along, basically, right? We've been talking about ions and how ions pair together, and we've been talking about redox reactions and when electrons hop back and forth between metals or different elements, things like that. And so now we're trying to get an idea about where those electrons begin and where they might be able to end, and how bonds are formed and made and all that kind of stuff along the way, right? So that's kind of the vision for the next 2-ish or so chapters. I would say 2-ish more chapters to go. It's a pretty important topic. You guys will use it a lot in organic chemistry. You'll use it a lot in biochemistry. Pretty much every chemistry from here on out. You guys will be seeing these kind of ideas over and over and over. It's one of these core fundamental concepts that comes up. Right? But before we kind of launch into it, we'll get started with prayer, and then we'll carry on. But Lord, we just thank you for another day, and we just thank you for another opportunity. And Lord, we just thank you for just putting on our hearts the things that you would have us think about, Lord. We just pray for that, Lord. Just put our minds in the right place. Just clear our thoughts, and just help us to be able to just to focus on the things that you would have us focus on, Lord. Just keep us from getting distracted with everything in this world and things around us. Lord, just help us to seek you out more each day, Lord. And Lord, we just pray for all the students who are not feeling too well, and the people who might be out and just kind of dealing with the COVID stuff, Lord. We just pray for them. We pray for their healing. We pray for everyone around the world that's being affected by this, Lord. We know that you're the ultimate healer, and we know that you're the ultimate doctor, Lord, and we know that you have a plan for all of this, Lord, and we just eagerly await just the beauty that you're going to bring from this situation, Lord. We just pray all this in your name. Amen. All right. So, where we had kind of ended up, we had ended up with this idea of how to walk through the different levels and the different blocks of the periodic table. And we had started to do a couple examples, I believe, where we had, or where we were looking at the periodic table and kind of figuring out where the different blocks are and how we count across and how we hop over and all this kind of stuff, right? And I think I asked you guys to do what, like antimony or bismuth or something like that as homework, right? If we're getting to, accounting for 50 electrons, right? That's a lot of writing to get there. But we always started out in the same way, right? The 1s2, 2s2, 2p2, 3s2, 3p6, blah, 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 right? All this kind of stuff to get to whatever element we need to get to. We hit our D block here, right? Our transition metal block, and we kept in mind that our quantum number steps down 1 here, right? If we number 1 through 4 here, then we have our 4s2, we hop down to our 3d orbital shell there, our 3d subshell, right? How many d orbitals are there?
5.
There's 5, right? How could you guys get 5? What different ways could you guys get 5? Oh, I just memorized it, Dr. H. Okay, well that's fine too. Okay, but how could we use a periodic table to help us figure out how many orbitals there are? Yep.
There are 10 sections, so I guess you just cut it in half.
Yeah, there's 10 rows, right? Scandium, titanium, all the way over to zinc. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? It takes 10 electrons to make our way through that D block. How many electrons can live in a single orbital? 2. So what's 10 divided by 2? 5. Right, you guys with me on this one? Right? How no, not 6. That's all right. Remember, you can always use calculators, right? So remember, the other way we can do this is using our quantum number L, right? Our quantum number L. If we're in our D subshell, that means L equal 2. And so -2, -1, 0, 1, and 2 gets us to 5 D orbitals, okay? Either way you guys want to approach it, right? The periodic table tells you all that information. We just have to remember how many orbitals can fit into a single orbital, right? And then we hop over to our P block and we get through all that kind of stuff, right? And so we could kind of, why don't we go ahead and do it? Why don't we start off with, doing something the hard way, and then we'll kind of show the somewhat easier way, maybe. So let's clear some space here. No, that's not what I wanted at all. Not duplicate, but delete. All right, cool. So let us clear that off. So let's do selenium here. Why don't you guys bust out the long form electron configuration for selenium?
Let's bust out some too while we're at it.
Michael, legitimately, are you okay?
Yeah, that's kind of the point. Yeah, that's true. But it's also practice, right? These are the exact questions you guys can expect on exams and quizzes, right? The configurations. So. Yep, that's good. Okay. Where'd you get that from? Yeah, remember you're just moving left to right.
Yeah.
Yep. Easy peasy, right? Okay. No, that's a 2S. We already did 2S. Yeah, just because we're moving left to right. You already have your 3S here, right?
Oh, yeah,
So.
okay. Thank you.
Cool, good. Yeah, that's one of the big problems with these types of questions, all these kind of clerical errors that might come up in there, right? Cool. So we're just hopping our way through, right? So once we're done with our 2S's, we hop all the way over to boron. Right? So our 2S, we basically hop that gap and go over to boron, where our P block is. So we give you our 2P. Going over here. Okay. Okay. Check the video that I posted for you guys, right? Cool. So it looks like we're well on our way to kind of understanding this stuff. Oh, I forgot the P that you guys were. Kind of ignore the right hand side of the video. Well,
lost.
you're lost.
Does.
Well, we're in Florida. If you go, oh, no, sorry. I got that.
There's one.
The good thing about being in Florida is you can't get too lost, right? Because in 3 directions you run into the ocean. So, and in 1 direction you run into Georgia. I'm just kidding. Anyway, so we have to walk our way over to selenium, right? So we start at the top. We always begin in the same place. I'm not going to change colors for each block here because then it really would take like 20 minutes, but hopefully you guys can follow along with me here, right? Let's do, there we go. So 1s2, right? We always start at the beginning there, start with hydrogen, 1s1, helium, 1s2, down to lithium, right? Beryllium, 2s2. We hop across the boron, right? 2p, 1, 2, 3, 4, 5, 6 there in the blue. So we got that. Now we're done with our 2s. We hop down to our 3s, 3s2, 3p6, okay? 3s2, 3p6 puts us here at our buddy argon, okay? From argon we hop down to potassium, 4s2, we get the calcium. We hop our way across the D block. So don't forget 3d10, right? We take a step down, right? And work our way across the D block there, all the way at zinc. And then gallium, right? Germanium, arsenic, selenium. So 4p4, right?
Right.
Yep.
If I make the letters capital, is that a problem?
No, not for me. I know what you guys are saying. So technically there is a difference, right? Capital D does stand for something already in chemistry, so we use lowercase d's for this. But I know what you guys are saying, right? Not too bad, right? So what's the worst part of this? Having to write it all out, right? So let's find a way not to be lazy, but to be calorically efficient, right? So let's try and shorten this up a bit. And the way we do that is by doing the noble gas kind of shorthand here, is what it is, okay? So our noble gases, remember, are over here on the right-hand side. We don't really do much with them. We talk about them and we use them as kind of a reference point to say, hey, when we're predicting charges, we want to get over here to our noble gas, that kind of thing, right? So we use them quite a bit, but we don't really talk about the chemistry of them too much. And that's because, honestly, there's not that much chemistry that I really know with them either. But they are kind of important for us in terms of, like, let's say reference points or ways to help us figure out principles or ideas. And so what we'll do is this. If I want to get to selenium, right? So what we just did. If I want to get to selenium, I'm going to pick the noble gas in the row above it. Okay? So I'm going to pick the noble gas in the row above it, which would be my buddy argon over there. Okay? And what we do is we put argon in brackets. Okay? And that's going to represent that the electron configuration for that noble gas. All right? So in brackets, we're essentially saying, let me change colors here just for emphasis sake maybe. Purple sounds good. Okay? So when I put those brackets around my noble gas, I'm basically saying this is what I'm shorthanding. You guys with me on that?
Yep.
That's the electron configuration to get to argon. Good? So that's all it is. So pick the noble gas above it, that's what we put down, and then we have to finish it up and put the rest. So we just do 4s2, 3d10, 4p4. Okay? So a lot shorter, right? So the noble gas configuration, the noble gas shorthand, whatever you want to say, that's all we're doing with it. Noble gas above it, put that in brackets, and that represents the electron configuration to get there. Sound good? So I think there's a couple examples in the slides for you guys to kind of work through here. I mean, it's practice, right? You guys don't have to do it now, right? But that's the idea here, right? Argon represents that configuration, so we just put the electrons that are not represented by that shorthand at the end of it there. And that's typically how we do it. Now, the benefit of this is also we're going to use this, or we're going to have, let's say, the same concept come back when we talk about the different types of electrons. So pretty soon we're going to launch into the idea of valence electrons versus core electrons. And the noble gas configuration there is going to help us just kind of make a help us distinguish between those two. Okay? So that's just kind of a little view of where we're going to go here in a bit. Here's kind of a little abbreviation of what we've been doing so far, right? When we get to D, it's n minus 1, it steps down, right? If we have, here's an example for 10, right? We can just go through and we can do that also there, and you guys can fill it in on your own, right? So these two slides just kind of summarize the examples that we've been doing in class, okay? So good slides to kind of study off of and remember, you know, kind of the methodology that we're going to have to answer these types of questions, okay? All right. So, I could ask you guys about the electron configurations for the transition metals, and you guys should be able, oh yeah, sorry, what's up?
Yeah, what do you do for these bottom ones? Are you never gonna ask us about those?
Yeah, I think that's a fair statement. We don't treat those any differently, right? We wouldn't treat those really any differently. I'll give you guys an example in just a second though. So ask me in maybe about, as soon as we're kind of done with this section. But in brief, we don't really do anything different with them. They're just kind of oddballs, and I'll show you what I mean with that, okay? So I could ask you guys for the electron configurations for the noble gases, and on paper, it doesn't really look all that different, right? But you'll notice I'm already kind of hedging my wording here, and I'm kind of, you know, fumbling around a bit, because there's going to be some odd stuff that happens. Now, that odd stuff that happens is going to be useful for us. When?
Gen Chem 2.
Actually, no, not until way later, right? In biochemistry, this might be useful for you guys, okay? So we're kind of setting up something that I'm only asking us to remember for 3 years, okay? Don't worry, as soon as you go back to that class, whoever's going to be teaching it at that point will kind of just have to poke at you guys again and say, hey, do you guys remember this from Gen Chem? And you guys are going to go, ooh. Then they're going to say, who do you have for Gen Chem? And you're going to go, right? But so we're kind of just setting something up that is actually an important idea, right? What we're about to talk about kind of helps explain where colors come from and all this kind of stuff too. So pretty important. Unfortunately, we'll need a little bit more before we kind of get to that part of it. Anyway, if I asked you guys for nickel, you guys would come up with this electron configuration here, right? Argon 4s2, 3d8. And if you put that down on the exam, right, you get a thumbs up. And everything's fine, right? Now, if you guys are looking on your periodic table, right, copper is right next to nickel. So you would say, okay, argon 4s2, 3d9. But there you'd actually get a point off or so.
Why?
Because things change, okay? So there's a couple of exceptions that happen in the transition metal block. Now, this isn't too surprising for you guys, or it shouldn't be, because we remember that when we were doing ionic charges, right, what did we say about our transition metals?
They suck.
Well, they're variant, right? They're variant, but there were even some exceptions in that variant block, right? Like zinc, right? Zinc was an example of an invariant metal in the variant metal block. And when we're doing ionic charges, what are we dealing with? Just the gain or the loss of electrons. So now that we know where our electron configurations are, we should start to be able to explain some of these exceptions to the rules in the transition metal block, okay? So that's where this is coming from. So a couple of examples that we're going to go through here just kind of talks about where we see some of these oddball rules come in for the transition metals, maybe is what it is, okay? The actual electron configuration for copper, or what we would expect you guys to put down, is that it would be 4s2, or excuse me, argon, 4s, well, let me do this here. All right, so this is what we would expect it to be, 4s2, 3d9, right? In reality, it would be 4s1, 3d10, okay? The difference here is what? I take one of these S electrons and I put it into my D block. Why indeed, right? Yeah, what's up?
Was it because zinc is next to it, and zinc is one of the exceptions?
You're thinking along, you're on the right path here, but then my immediate question would be is why is zinc an exception, right? But your answer is, well, wait a minute, we notice there's something special that happens at that position, right? So that's a good observation. And that's the thing to pay attention to. What is different here? What is the big difference? Well, here we've got a 3d10. Huh. How many d orbitals do we have? 5. How many total electrons can fit in them? 2 each, so a total of 10. So do you guys see what happens when we promote one electron? We make a complete filled subshell, right? You guys see this? We make a filled subshell. And that is a stabilizing of influence on the electrons, on the atom. That lowers the energy of the atom itself, okay?
So do you do that when the, like, let's say the S block before it, do you only do that when the S block would not equal 0? Like, you have a 9 and a 2, so you put 1 in for 10. But when you have 8 and 2, you take the 2 out to make the...
The answer is, we typically see it most when we can only move one electron around.
Oh,
There are some exceptions where you might take all of the S and put it into the D, right? I think the next slide actually shows you guys that, but that's a little bit less common, right? Yeah.
So is this concept gonna be true for silver and gold as well?
It kind of is, right?
I don't like.
It's okay, right? But there, and so like I said, on the next slide, I think it's the next one, I'll show you guys where we see these exceptions, right? So what we need to start to pay attention to is kind of this idea here of, hey, if I can promote an electron, or I can fill a subshell, that's going to be a stabilizing effect for the atom itself, okay? So that's what we're going to be looking at here. So here, right, and highlighted in gray there, are some of these exceptions that we might run into, okay? So I think this might answer some of the questions that you guys had there, right? You notice palladium, we would just say has 4d10, right? So we put all of our S electrons into palladium, okay? That's kind of an oddball though. But you'll notice here, what, copper, silver, and gold, what do we have there? We have that same exception to the rules, right? We take one of our S and put it into our D, okay? And so we make a completely filled d orbital set. And what do you notice about chromium and molybdenum over here?
They have half a set?
Right?
What's the deal with rubidium and rhodium? Why are they dropping to 5s1 instead of 5s2?
Here for those?
Yeah.
Yeah, good question. No, it is a good question, right? So there's something else going on behind the scenes too, right? But what I'm trying to get you guys to look at is the patterns here, right? We're seeing that when we can make half filled and fully filled, those are the ones that we're going to see most commonly behave that way. There are some other oddballs in there, and we could spend some time discussing that, and we do. All you got to do is come take my inorganic class, and we'll walk through that stuff, okay? Patterns is the key, though. Well, you guys are mostly all here interested in doing some kind of science, right? One of the key parts of science is doing what? Recognizing patterns. And then you have to ask the question, well, why in the world does that happen, right? So what we see here is that there's a stabilizing influence at half and fully filled orbital sets. What's up?
Why does the d orbitals already the s orbitals? Like,
Oh, that's just kind of one way of, I just did that for emphasis is all it is.
well, I mean, how does it make it any more stable?
Oh, and
S
that, I thought
has-
you meant the way I wrote
Now
it.
s has 1 instead of 2. Isn't that half of a...
It's because of the way it stabilizes the orbital, or something called exchange energy, which basically says, if everyone in here had the same apartment, right, the same orbital, what can happen is electrons can go to visit their friends in those different apartments. And the more friends they can visit, the more it stabilizes the orbitals, is what it is.
Okay.
So exchange energy. Basically, electrons hop around as well. And the more you can, but in an S orbital, there's only one of them. They can't hop anywhere, right?
Okay.
They can't visit their friends.
So start isolation.
Yep, they're in quarantine. That's right.
Is gold a typo?
Is it?
The S?
Oh, yeah, that's a good call. Yeah, that should be 6S. Yeah, sorry about that. I didn't even catch that. Magically, we bring our 4S orbitals back. No. That is absolutely a typo. Good call. All right.
No, it's.
Yeah.
it's-
Wait, let me argue this. I can't make mistakes. No, you're wrong.
It's an exception, obviously. That's science.
But there it is, right? Cool. Now, well, I think I've beat this to death already. I think you guys got it. All right. Okay. So now that we know everything there is about dealing with the electron configurations of elements and individual atoms, right, now we go and take the approach of how we deal with ions. Okay? So if I ask you guys the electron configuration for these ions, the way you approach it is you do the electron configuration for the neutral element, okay? And then you just take or add one more electron or two more electrons or whatever it might be. Right? You continue walking through the periodic table as you would normally, okay? So, if we're dealing with sulfur, right? What's the electron configuration for sulfur?
16.
That's how many electrons it has, right?
Configuration would be, I have the brain, hold on. Neon,
No, you can go ahead.
neon, 3S, 2. My brain hasn't woken up yet.
3s2, what's the rest of it? Okay. 3p4, right? So that would get us there. So what does it mean to be s2 minus?
It means you have 2 extra.
I'm adding 2 electrons. Can I fit those 2 electrons in my p orbital set?
Yes.
Yes, right? Because I only have 4, and we can hold a maximum of
6.
6. So what would the electron configuration be for s2 minus then?
The same
The
thing
same
as
thing
that,
with 3p6.
except with the p6.
Yeah.
Our brains are almost.
Why do I keep doing this? That's what.
Relaxed speech.
Good.
Can you explain that one more time?
Yep. So what I did is take the electron configuration for sulfur, right, and then I add 2 electrons like I'm continuing to walk through the periodic table. Right? So here's sulfur. I add 1 more, I add 2 more, right? What do you guys notice about the electron configuration about the sulfide ion?
It goes to a noble gas.
It does, right? In fact, it has the exact same electron configuration as, what noble gas is it?
Argon.
Argon, okay? Is that a coincidence, or is that how we kind of learn to predict ion charges? It's kind of how we learn to predict them, right? So now we can go back and explain exactly where those ions go to or where they come from. So do it real quick for rubidium there.
And just because.
If you could, Alex, if you would subtract 1.
No, because. And it's plus, see, it's right.
Yeah, I know it's plus.
So it would just be 15.
Oh, wait, it's hard to do.
Yeah. Oh, yeah. It's just. All of your chemistry jokes are bad.
Right? So if I do my electron configuration for rubidium, that's what it would be. when I remove an electron, I take the last one, right, at the end, out of it, so I lose my S electron there. Right? Which puts me at the electron configuration for
Krypton.
another noble gas, right? You'll notice in all of these cases, we have what? P6. How many electrons can we fit into our p orbitals, our p subshell? 6. Right? So do you guys see how this is very similar to this idea of what we just talked about there with the transition metals? If we make a filled orbital set, right, that's some kind of stabilizing influence on the atom, right, the orbitals, the electrons. So same idea here, although on a lesser scale, right, on a smaller scale than what we might expect with the d orbitals. We don't see any of these transitions from the s to the p's as we do in the transition metals there, okay? But it does help to start to explain why noble gases don't react in the same way that we might expect. Okay, we have these orbital sets and they're filled, and right, and so they kind of have a special stability is what it is. Okay. Cool. So if I ask you guys, and you should be able to do the electron configuration for all of these, okay? Then what you guys will see is that they all have the exact same electron configuration, right? And so we would just call that isoelectronic, right? Iso meaning the same, right? And electronic just dealing with the electrons, right? So the equal number of electrons and the same electron configuration is what it is, okay? But again, this shouldn't be anything too different from what we already expect, because this is basically just playing the game of, hey, what are the expected ionic charges for these individual atoms, right? Just get to the nearest noble gas, whether you gain or whether you lose electrons to get there, okay? Yeah.
So by saying that they have the same configuration,
Yeah.
how is that possible?
How?
Like, do you mean like the last one is the same? Like it's always P6 or something?
Yeah. Well, they have the exact, right? If you go through and do the electron configuration for all of these, it'll always be that answer there.
Okay.
Right? They have the exact same electron configuration. That doesn't mean they have the same properties, though.
Okay.
Right? Because you'll see, you know, calcium 2+, we would expect it would behave a lot differently than something with a minus charge. But they do have the same configuration. Yep.
How come it's written out as helium-2s2 2p6 instead of just neon? And like, why is neon through to
You could do that, but typically, if we're dealing with electron configuration for a noble gas, then you use the noble gas before it, right? So it's just, remember with the shorthand method that we learned, you always take the noble gas from the row above it, right?
So for krypton, you would use argon and then fill out the rest of it?
Yep.
Okay.
Yep, that's how it is.
That seems kind of concerning.
No, there's a reason for it, right? And the reason has to deal with what will, these different types of electrons that exist, okay? Time consuming. It's like, oh, it takes like 30 seconds, Dr. H, you don't understand. I've got things to do.
I've played video games my whole life. I have an attention span of exactly 3 microseconds.
Uh-oh, not good. All right. So let me scroll this down just a bit here. So here we go back to our transition metal ions. And if you guys haven't gotten the point yet, transition metals behave a little bit differently, or maybe a little bit unexpectedly. So if I ask you guys to do the electron configuration for, you know, Fe2+, right, iron 2+, iron 3+, or any of these, okay, we might suspect that we would just go through, do the electron configuration for the neutral atom, and then remove the last electrons that we fill in. And that would be great because that would follow the pattern, right? But it doesn't work that way. Because life is full of small challenges for us to overcome, right? So what do we do with a transition metal? Okay, when you're in a transition metal, your S are always lost before your D orbital, your D electrons. You're always going to lose your S electrons before your D electrons.
Aren't the S electrons close to the center?
Maybe.
So then why are they lost first?
That's the way the world works.
Doesn't it depend on,
That's a good question. swing by my office and we can explain that. It's that you're like, wait a minute, that doesn't make any sense. Remember, what did I always say? I just lie to you guys to your face, right? And now it's on camera. Oh man. But that is a good observation. There's got to be something else going on, and there is. Okay. And when are we going to learn it, Gabe? No, this one's again in inorganic chemistry. Sorry, that's twice in a row you've got it wrong. Right?
There's so many gen chem to organic chemistry,
Yeah.
inorganic chemistry, biochemistry. How are we supposed to predict which one it's gonna be?
Yeah, you just got to take a guess. For what it's worth, I'm technically an inorganic chemist, so there's only so many worlds that I can walk in, right? So that's a good choice to usually pick
You've
inorganic.
said biochem twice in this class.
Yeah, biochem is though, right? So yeah,
That is
nobody
my
wants
favorite.
that. What is it? Oh, a protein? What's it look like? A glob? No, I'm just kidding. No. But anyway, so the important part is when we're making ions, right, from our transition metals, take your take your s electrons before your d electrons. Okay? So if we have our electron configuration for iron, if I say iron 2+, I take away my s electrons first. That's all there is to it. Okay? So real quick, if I ask you guys, right, to take a look at the electron configuration for, right, electron configuration for silver 1+, okay? So for silver 1+, what would it be?
Is this gonna be one of those exception things?
It might be, didn't we just talk about it?
Mm-hmm.
Mm-hmm. Isn't the electron configuration on one of the previous slides I gave you though?
Yeah.
Right?
It would have to be a free library.
So you lose your S before you do
Yeah, but see, it's gonna be 4D, not 4. No, it's gonna be 4D, not. So it's there. Yeah, because that's the exception.
Oh, right, because, okay, I see what you're saying. I thought you were saying. Yeah.
We have brain cells with Why do I
But-
have much?
Is silver one of the exceptions of the transition metal thing?
It is.
So does it accept the exception?
No. Remember what, like we said, we get the electron configuration for the neutral, and then we just lose the s electrons first,
Okay.
right? So, the same thing that we've been doing, we just have to remember that the neutral atom is an exception. Okay? So neutrally, right, we would say krypton 5s. Right? 5s1, 4d10, right? For neutral silver, and then we take one away, but we lose our s electron first, okay? So the electron configuration is 4d10.
That would be a good stat roll.
Yep. Let me ask you guys a question. What do you think is the most common ionic charge for silver?
1.
Why would you say +1? Because if you lose one electron, what are you left over with?
4D10.
And what's so special about having D10?
It's a complete D shell.
It's a completely filled D shell, and there's some kind of magical stability that's associated with it, right?
Because none of the electrons want to go.
Does that make sense?
Yes.
I'm not saying that it can't exist in other oxidation states. I'm saying the one it prefers to is just to lose one electron to get to our D10. And very commonly, there's actually very few exceptions of where silver isn't a +1. When it isn't a +1, it hangs out as a +3 usually. But there's a different reason for that too, okay? Does that make sense? So now we can start to tie together our ionic charges, right, with certain preferred electron configurations. Okay? In fact, I could ask you guys the same question about iron 3+. Iron 3+ is what we see the oxidation state in rust. Okay, is rust very reactive? No, it's just going to kind of sit there, right? We got to do a lot of work to make rust do anything. Why would iron in the 3+ not want to gain or lose too many more electrons.
Cause it's already halfway.
It's at a half-filled orbital set, right? Which imparts some kind of magical stability. Okay? Does that make sense? We start to see these patterns, and we can explain these patterns based off of the electron configurations. What's up?
So is iron 3 plus and manganate 7 plus, is those like the maximum charges that those elements can have ionically?
For manganese 7 plus, yeah, you can't go, because you're only dealing with core electrons at that point.
Okay,
Right? You can't lose any of your noble gas electrons if you want to think about it that way.
okay.
But yeah, we can actually see other oxidation states for iron. In fact, in your body right now, there's iron existing in the +4 oxidation state.
Whoa.
And this stuff, a very important thing called your cytochrome enzymes, right? Yep. And you guys can learn about that in,
Biochemistry?
it's inorganic, no, I'm just kidding, yeah, it's bio.
So hold on, and just another thing.
Yep.
So, for any of these, like, once they reach plus or minus,
Mhm.
the configuration for noble gas,
Yep.
they can't go any further.
Yes.
Okay.
Yeah.
So they can only go as far back down as the previous noble gas,
Yep.
Or as far up as
or as
the
far up as the
next.
Well, we have to be careful with that one, right? So we'll talk about where we can kind of look at this. Remember, for anions, we add electrons. So there's a preferred, right? There's a maximum we can add, right? When we lose electrons, there's a maximum we can lose, if you want to think about it in that way, right? But there are exceptions along the way to get there, right? No. There's always, remember, there are exceptions, but remember, what we need to start thinking about is that they're not so much exceptions as there's got to be some kind of predictable pattern for it, right? So that's what I'm really trying to teach you guys for the next 5 years, 6 years that you're here, right? All the patterns. No, don't let it. Why don't you roll your eyes? You guys don't want to learn everything, man. Right? But that's what it comes down to, right? Starting to pay attention to patterns and explain why these exceptions are. Right? I know you guys don't like these exceptions, but that's what makes science science, right? We learn something new and say, well, why in the world does that happen, right? So it keeps life interesting, right? That's why I get up every day, okay? Find new patterns, okay? So now we're going to talk about 2 different types of electrons. We're going to talk about the electrons that we care about and the electrons we don't care about, okay? Now that's kind of a way too blunt of a statement. Obviously all electrons are of equal importance. However, the valence electrons are the ones that are going to do stuff for us. They're the ones that are going to make bonds. They're the ones that are going to hop around and change charges and these kind of things. So the valence electrons are the ones that are important, okay? And valence electrons are arranged in the shells there, in the subshells. That's what Lewis said, right? Periodicity, elements with similar properties have equal number of electrons in their outer shell. We've been, I think, harping on this all semester long, right? Hey, look, if there's stuff in the same family, we expect similar reactivity, and now we can kind of put a fine point on that by saying, because they have similar electron configurations, and because they have a similar number of valence electrons, therefore we would expect them to behave in the same way, right? So not too long ago, right, the periodic table that I gave you guys there is somewhat antiquated, right? They finally identified and isolated all those unknown elements on the periodic table, right? And
All of them?
Up to 118 there, right? The UUO that's on the one that I gave you guys.
So they still don't know what UUO is?
No, they have it, right? They've isolated, they've made it, right? They've identified it. It exists for, femtoseconds or something like that, but that's apparently long enough for them to have made it and to, get their science publication out of it, right?
So why is it so unstable that it only exists for such a
Yeah, good question, right? When will we learn about that?
inorganic?
No!
Chemistry.
And that's an interesting question, actually, right? Because there is some instability that comes along with making these larger nuclei, right? Which you guys already knew, right? Because uranium and plutonium, all these things, they naturally decay to smaller elements below them, right? So there's got to be some kind of, the glue that holds the stuff together has to be weakening as you add more things in there, right?
Is it because how with electrons, the closer they are to the nucleus, the stronger they are, or the stronger the bond, right?
They're the tighter the attraction, you would say,
Right.
yes.
So as the nucleus grows bigger, is there something in kind of the center of the nucleus that as it expands away from it, even the nucleus itself starts to fall apart to a smaller nucleus.
I guess you could think of it that way. Right? But anyway, so what was I yammering on about? The periodicity there, right? So taking a look at the similar valence electron shells, okay? So what in the world is a valence electron? There are electrons that are in the outer shell. These are the things that we've been doing, right? These are electrons that we've been identifying when you guys are using the noble gas shorthand for writing your electron configurations, okay? So if we go back to an example that we just did, right? For sulfur, right? We said, what was it, argon or krypton? Which one was it for sulfur?
It would be neon.
Neon, okay. Oh, getting ahead of myself. Okay. So we have neon, right? 4s,
No,
3s. One ahead of myself. 3s, 2, 3p4, right? I got that in the first try. All right. Right? So there would be our electron configuration for sulfur. The 3s2 and the 3p4 is what we would consider our valence electrons. Okay?
Oh.
They are the electrons that are in the outer shell. They are electrons in incompletely filled shells. Okay? How many electrons can fit into our p block?
6.
6. Do we have 6 electrons there?
No.
No, so it's incompletely filled. Got it? And it just so happens that our s electrons are pretty much always going to be valence electrons too. Okay? That should be a little bullet point that you guys add in there. S electrons are pretty much always valence electrons. In fact, I can't really think of an exception to that, right? But if you guys find one, let me know. Yeah?
So could the core electrons also be considered the electrons that add up to the previous noble gas?
Well, that's exactly what they are, right?
Okay.
Yeah. Partially filled d orbitals, right? They mention that kind of separately in the book and all that. I don't really know why, because if they're an incomplete shell, right, then, you know, if it's a partially filled d orbital, right, then, well, it's that's still an incomplete shell, right? So that's kind of redundant. So basically what you're looking for is your s and any partially filled orbitals is what it is. Those are your valence electrons. Let me ask you guys a question, okay? If sulfur loses all those electrons, what charge would it have?
Positive 6?
Plus 6, right? And that would put it at a noble gas configuration, right? So if I lose all my valence electrons, I would get to plus 6. If I gain 2, right, I would make my noble gas configuration also, right? So plus 6 to minus 2 with my ion charges there. You guys with me on this? What's the difference from plus 6 to minus 2?
8.
8. Is that just a coincidence?
No.
Maybe, maybe not, right? So let's think about this in a different perspective here, right? So let's think about our buddy carbon, right? So we have 1s2, 2s2, 2p2, right?
Is helium not considered a noble gas?
We could, I forget what the noble gases are, so it's easier for me to write it out. It's the one, I don't remember what the order for those are, we just don't use them, right? I know helium's first, and then I just
saying how important they are.
I say they're important as kind of like landmarks, right? But we don't use them in lab that much. I'm sorry I've let you down. I can tell I've disappointed you. Many apologies. Anyway, so here's our electron configuration for carbon, right? What are the valence electrons for carbon?
Just
4. No.
2s2, 2p,
2s2 and r,
2p2.
2p2, right? Here are the valence electrons. Why? It has 4 valence electrons, correct, yes. Right? Our topmost orbital shell, right, the s and any partially filled orbitals are the valence electrons, okay? What charge would carbon have if it lost all of the valence electrons?
Positive 4.
Plus 4. How many more electrons could we give to carbon to get it to the next noble gas up though.
Also 4.
What's the difference between +4 to -4?
8.
8. You guys starting to see a pattern here?
Yes.
Right? Is that a coincidence?
I think not.
There's got to be some kind of explanation why we keep getting to this 8 number, right? What are our valence electrons typically? Our S, right? And then our examples here, what are they? R, P. How many electrons can we fit into our S? 2. How many can we fit into our P?
6.
What's 2 + 6?
8.
You guys with me on this? You guys see the pattern here?
Yes.
Yeah.
Right, what we're going to talk about, and I'm going to keep harping on something called the Octet Rule, okay? The Octet Rule just basically says get to the nearest noble gas, but the reason why it's 8, because that's how many we can fit into our S and our P orbitals. You guys with me on this?
Mhm.
What's that?
So what's the rule for transition metal?
It's different.
Is that
You lose your S electrons first, right?
Right, but the D thing has, like,
10.
the full shell is 10.
Yeah.
So that's not a factor.
If you have a full d orbital set, you probably won't lose those, right? So take a look at the partially filled, right?
Okay.
That explains why zinc behaves the way it does.
Right.
Right, it'd be 4s23d10, it can lose those S, because our S are always gonna be valence,
Right,
but it's gonna be really, 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 really difficult to lose any of those D electrons,
okay.
because it's a filled orbital set.
So the transition metals seek to have 10 or
Mm.
5.
No. Yes and no. Yes overall, but not in the way that you're thinking, right? Well, I think what you're asking is, will it only lose electrons to get to like the half-filled orbital? The answer is it might prefer to stay there, but it can lose those also, right? Here's what I mean. So if we go back to this example right here, right? I asked you guys the question, what can we tell about iron in its 3+ oxidation state? It's that half-filled shell, and that's a stable oxidation state, ionic charge for iron.
Right.
But we can see other ones exist, right? But this is kind of its happy spot because we see that half-filled orbital, but it can still lose those,
Okay.
right? So it does impart some kind of stability, which makes it more difficult, but that doesn't mean it can't happen,
Okay.
right? Because we are still in this rule here. That is still a partially filled D, and so that falls into our valence electrons
Okay.
definition.
But it kind of same question thing. So what about, like, do they seek to have 10 if possible instead of 8? Like, is the value for transition metals, the value that they're seeking, more connected to the number 10 rather than the number 8, like these guys, because of the fact that, like, they don't have the whole S and P thing? Like 8 isn't important.
With ions, no,
Okay,
right? With neutral atoms, that would be a fair statement,
okay,
right?
okay. Thank you.
Yep. Okay, so last thought here. If we aren't a valence electron, we're a core electron, we don't deal with anything with core electrons. I'm not saying we can't do anything with them. In fact, there's some important analytical techniques that we can do, right? But we're not going to be dealing with anything with them here, okay? So common questions would be to identify your valence electrons and identify your core electrons. If you're not a valence, you're a core. If you're not a core, you're a valence. Got it?
Mhm.
That's all there is to it. Okay, so here's just a couple examples for you guys to work through on your own, or to, if you guys just want to look at it, right? So write out the configurations, right? You do your core set, and then anything that's not in your core set, there's your valence. What's up?
So again, for like the condensed, when you're writing the
Yes.
electron configuration, it's
Yep.
just, it's in that row.
Yes,
Okay.
depending on the block that you're in, right?
So, for anything that's down, past where the D block starts,
Yep.
we consider our G shell part of the core?
Yes,
Okay,
right, because if it's filled,
if it's filled.
right? If it's partially filled, then it's a valence. What's up?
So we just started wherever our S is, or it's like, alright, we're starting here and we go down. And
Yes.
Those are our valence electrons, right? Unless we have a 10, and then we're like, nope.
Yeah.
Okay.
Remember there's not that many rules, right? The rules are, they're your S electrons or anything that's in an incomplete shell, right? Cool. So now we start to get into a little bit of something that we'll be using quite a bit.
Magic dots.
Sort of, right? So when we start to use our valence electrons in our atoms to build molecules, right? Our valence electrons are the ones that are going to do that for us, okay? And so the way we start to draw molecules are what's known as Lewis structures, right? Lewis being the guy who kind of came up with this system, right? Now, the way we represent this is we just simply put dots surrounding the symbol for the atom itself, okay? So you guys should be able to get the electron configuration for nitrogen, and you'll find that it has 5 valence electrons with it. Okay? And we just represent those 5 with dots around them. We typically start by spreading everything out before we pair it up, just as convention. And what I mean by that is, if I were to draw this out, I would put my nitrogen, and then I would say, put 1, 2, 3, 4, and then I would come back and pair it up.
So it goes clockwise from the top?
It doesn't matter whether it's clockwise or counterclockwise, just we have it as individual, and then we pair it up, okay?
Okay.
So, is that representative of the spin notation, like having the half arrow, half arrow?
Yeah, it's probably related to that, yeah, in some way, right? You're talking about the Hund's rule there, right?
Right.
We spread everything out and then we pair it back up. What you'll find is I'll go ahead and give you the preview that I'm lying to you guys about this stuff.
Oh.
Right? So,
That
but
helps.
this is a fantastic lie though. It is an extremely good lie because now we can start to explain a lot of stuff by drawing it out, right? So I'm not saying we lose information by doing these kind of shorthand things, but it's extremely valuable because you can literally do it right in front of you no matter what structure you guys have.
Right, because it's more in depth than just dots.
Absolutely, absolutely. And we'll learn a little bit about that depth as we go through, right? But it's a good question, right? Why do we do it in that way? The answer is convention sometimes, right? Cool. Okay, so now here's a question for you guys, okay? Here's a question for you guys. How many electrons do I have to add to nitrogen? How many electrons do I have to add to nitrogen to get it to its nearest 8? 3. Now what we're going to talk about in just a bit is that every time you make a bond to an atom, you add an electron to it. So how many bonds might we expect to see to nitrogen in its happy state? 3. Are you guys with me on this one?
Mm-hmm.
Right? And I could ask you guys the same question across almost the whole row here. Carbon starts out with 4. For each bond, it gains access to another electron. So how many bonds makes carbon happy?
4.
4. How many for nitrogen? 3. How many for oxygen? 2. How many for fluorine? 1. You guys with me on this?
So is that what makes carbon in everything? The fact that it is able to have so many different
That's
combinations?
part of it, right? Yeah, we can make 4 bonds to it. Now the question might become, well, so could silicon, right? And there's another reason why, or there's multiple reasons why carbon is let's say the preferred element for life. Silicon can do a lot of the things that carbon can. In fact, it can do some things even better. Okay?
So is that why sci-fi shows have things about silicon-based life
Yeah,
forms?
no, that's it, right? Yeah.
Cool. Got it.
The chemistry is very similar for silicon.
We gotta do like a Star Wars marathon.
Right? And so if we take these ideas we've been talking about together here, the idea of electron configuration and ion charges and getting to 8 and all this kind of stuff, what we say is, well, the book talks about the Octet Rule. Okay? Now I'll go ahead and shatter your guys' beatific vision of who I am. Okay? The Octet Rule is a lie. Okay? I know. What happens is I want to go ahead and break your guys' hearts now because I usually have to do this in organic chemistry, and they're already far too deep into their biochemistry degree. They can't change it at that point. So now's your guys' chance. Okay, nobody changed. That's okay. Right? So the Octet Rule is you guys remember the Pirates of the Caribbean movies where they're like the pirate code, right?
It's more guidelines.
It's more like a guideline, right? In fact, I'll go ahead and tell it to you guys here. There's really only 4 atoms on the entire periodic table that exclusively follow the Octet Rule. Okay? There's really only 4 of them. All the other ones, it's more like a guideline. It's a good guideline. Okay? And it's the guideline that we just did on the previous slide there, where I said, hey, how many bonds do you think silicon would want? And you said, well, it's got 4 valence electrons, and it gains 1 electron for each bond, so I would expect 4. And you'd be correct. Most commonly, that's what we see with silicon. But silicon doesn't have to exclusively obey the octet rule, okay? But carbon, nitrogen, oxygen, and fluorine will, okay? Carbon, nitrogen, oxygen, and fluorine, we won't see any exceptions with those, ever. Asterisk. Right? For you guys, we won't see any, okay? For you guys, we won't see any. When you guys get to OChem, then we'll see a couple of those pop up. Okay? Cool, that's the end of chapter 6. Okay, lots of conceptual stuff in there at the end. Lots of important stuff that we're going to build 7 and 8 off of. So make sure you guys understand this idea of valence electrons and counting and all that kind of stuff with it.
Is our next quiz gonna be on Monday?
No, I gotta put the quizzes online, so I gotta get that set up for you guys, right? Because otherwise, no one's here. So lots of students are kind of, doing the quarantine thing or whatever it might be, right? So we're gonna have to change a little bit about how we do quizzes and exams.
So Wednesday or Friday?
I will let you guys know, right? I'm not gonna surprise this one on you guys because it's gonna involve you guys, probably using lockdown browser, that kind of stuff, right? So. No.
Just kidding,
Okay,
it's
so
Friday.
I will see you guys on Monday then.
Thank you, Dr.
I've never done that to you guys.
I know, well, I mean.